Module 1, Session 3. Module 1, Session 3 will cover the following content: revision of standard form versus polar form, learning outcome 1.1.2, perform multiplication and division on complex numbers in polar form, learning outcome 1.1.3, de Moivre's theorem. Let's pause the video to do another group activity. In your groups, discuss your approach to the following: revising polar form with students, multiplication and division in polar form, de Moivre's theorem. Include the following in your discussion. How do you explain this concept to your students? Problem areas, tips and tricks, important things to remember. You can draw diagrams in your workbooks if necessary. Before we start manipulating polar form, let's backtrack and do some revision. So what is polar form and how does it differ from standard form? Your students should remember from level 3 that we can represent complex numbers on a Cartesian plane. Real numbers are represented on the horizontal axis and imaginary numbers on the vertical axis, and we call this a complex plane. Students should remember that when complex numbers are represented on a Cartesian plane, we call it an Argand diagram. Here's an Argand diagram representing z is equal to 1 minus 2i and its conjugate z is equal to 1 plus 2i. Notice the rectangular shapes on the complex plane. This should help your students remember how to identify the rectangular form. Students should remember from level 3 that the other form of complex numbers, the polar form, can also be obtained from an Argand diagram. This graph shows us the relationship between the rectangular and the polar form. A is the real part of the complex number. B is the imaginary part of the complex number. R is the diagonal distance from the origin, and it is called the modulus. Theta is the angle measured anticlockwise from the positive horizontal axis, and it's called the argument. So how do we derive the equation for the polar form? We use our basic trigonometry. Notice the right-angled triangle. Your students should remember that with right-angled triangles, we can use our trig ratios to represent a complex number in terms of the angle theta. So we have cos theta is equal to the adjacent over the hypotenuse, and we get this from our trig ratio CAH, and this gives us A divided by R. Therefore, A is equal to R cos theta. And then we can look at another trig ratio, which is sine theta. This is the opposite over the hypotenuse, which comes from our trig ratio SOH. This gives us B divided by R. Therefore, B is equal to R sine theta. Now that we have values for A and for B, we can substitute these values into our equation for the rectangular form. We then factorize by taking out the R, and we get z is equal to R cos theta plus I sine theta. We call this the polar form of a complex number. It's important to remind your students that polar form can be written in different ways. They all mean the same thing. Learning outcome 1.1.2. Perform multiplication and division on complex numbers in polar form. When students are familiar with the concepts of standard and polar form, we can move on to multiplication and division. Students should remember multiplication in polar form from level 3 as well. Step 1. Multiply the moduli R1 times R2. Step 2. Add the arguments theta 1 plus theta 2. Here are two different ways to represent the multiplication of complex numbers in polar form. For division of complex numbers in polar form, step 1, we first divide the moduli R1 divided by R2. Step 2, subtract the arguments theta 1 minus theta 2. Here are two different ways to represent the subtraction of complex numbers in polar form. Let's watch a video of an example.
Simplify 48 cos 125 degrees divided by 2 cos 40 degrees times 4 cos 69 degrees. What do we have here? We have a combined multiplication division problem. We can do this in one step, but seeing that we're revising multiplication and division in polar forms, that's why I will first focus on the multiplication part at the bottom. So 48 cos 125 over 2 cos 40 degrees times 4 cos 69 degrees will now become, my numerator remains unchanged, but my denominator, how do we multiply two polar forms? Firstly, you multiply your 2 times 4 with cos. You multiply your modulus, which is 2 times 4, and you add your arguments, 40 plus 69. That is how you multiply. Let's simplify that. 48 cos 125 over 8 cos 109, because 40 times 69 give you 109. Now we have simplified the product. Now what do we have here? Complex number in polar form divided by another complex number in polar form. What is the rule there? You divide now your moduluses and you subtract 125 minus 109. You subtract your arguments. 48 divided by 8 is 6, cos 125 minus 109 gives you 16 degrees. Now, you can stop there, but the question just states simplify, so we need to play safe. Let's simplify then this to the standard form. What does that mean? Now you can reveal to your learners what cos means. 6, the C stands for cos of 16 degrees, plus I, the S stands for sine, still 6, 6 is common, 6 cos 16 degrees plus 6I sine 16 degrees. And now you can go to your calculator. 6 cos 16 degrees, and you can punch equal. You will get 5 point, we're going to round off to 3 places, 7, 6, 8. Then you clear. Again, 6 sine of 16 degrees, you close. That equals plus 1,654, very important, I. And that is your answer in standard form.
Learning outcome 1.1.3, de Moivre's theorem. Now, how do we go about raising a complex number to a power? To do this, we have to use de Moivre's theorem. This theorem is brand new content in level 4, so lecturers need to make sure that students really understand how to apply it. what does de Moivre's theorem state? If z is equal to r cos theta plus I sin theta, then z to the power of n is equal to r to the power of n times cos n theta plus I sin n theta. The alternative notation in cis form is given here. Let's look at the steps we take to raise a complex number to the power of n. Step 1. Raise the modulus r to the power of n. This gives us r to the power of n. Step 2. Multiply the argument theta by n. This gives us n theta. Let's now view a simple video example to start us off, followed by a slightly more difficult one.
Let's look at the following example. If z is equal to the square root of 2 bracket cos 45 degrees plus I sin 45 degrees, close bracket, determine z to the power 8. This power 8 tells me that we need to apply de Moivre's theorem. Also, in order to apply de Moivre's theorem, it is only applicable to the polar form, which is the case in this specific example. So we're going to start by saying z is equal to the square root of 2 bracket cos of 45 degrees plus I sin 45 degrees. Let's write this in a more simpler form. This is exactly the same as the square root of 2. Remember earlier on? Cos I sin 45 degrees. This means exactly the same as that. And it's important to note that. Now I'm going to solve z to the power 8, and it's much more easier to write it in this form, which is equal to, let's put it in bracket, the square root of 2 cos 45 degrees to the power 8. What does that mean? When you go for the power, that's your modulus. You raise the modulus to that power, and you multiply the argument with that power. And if you use your calculator, square root 2, divide by 2, because square root means you divide by 2. That's 2 to the power 4, which will give me 16, because 8 times 45, that gives me 360 degrees. And that is your answer.
Complex numbers in polar form, multiplication, division, and de Moivre's theorem. We are given 4 cis 120 degrees to the power 2 times root of 2 cis 30 degrees all to the power of 4 divided by 3 cis 20 degrees to the power of 2. To go about this solution using polar numbers, let us simplify the root of 2 first. What is next of us then, we're going to have to bring the power down to the coefficients, and then we multiply by the power as the on the degrees, on the angles. So the power comes down, raised as an exponent to the coefficients, and the exponent multiplies the angle. And then we bring the we bring the denominator. Same thing applies. What is left of us, just have to simplify. So we are given 6, 16. 4 to the power 2 is 16. That 16 must multiply with this, so 1 times 4 is 2. 1 times 4 is 4. Then 4 divided by 2 is 2. 2 to the power of 2 is 4. That one. To put all the solutions of your angles, 2 times 120, 240 degrees. These are multiplying each other, which means that the angles must be added. 4 times 30, you get 3, 6, 9, 12, 120. And then this one is going to be transposed to the numerator. You subtract 2 times 120. No. This is 20, not 120. Sorry. 2 times 20 is 40. My bad. 2 times 20 is 40. Also here, let's correct that. It's not 120, it's 20. Pardon me for that. We can see from here, 20, 20. It was just an error. Pardon me. And then we divide this by 3 to the power of 2, which is 9. It's a matter of simplifying this now. So we can straight away from our calculator get this. 16 times 4 gets you 65, divided by 9 gets you 7.11. So we get 7.11. Then we add this 240 plus 120, that's 360, full revolution, minus 40, that gives you 320. So our final answer will be 7.11. It says angle of 320. That's your final answer.
Let's look at some teaching tips on de Moivre's theorem.
Link de Moivre's theorem with polar form. What does that mean? You can only apply de Moivre's theorem once the complex number is given in polar form. Now, otherwise, and that's very interesting, what they normally do is they give it in rectangular form, raised to the power 8, for example. You're going to multiply your whole 3 hours in the final exam and still don't have an answer by just forgetting that point. It must first be converted to polar form. Just watch out for that.